we're going to review the Pythagorean theorem that you learned in 7th grade. The Pythagorean theorem is a theorem related to right triangles, and it's an equation that relates the sides of a right triangle. And the theory says this: if you square the hypotenuse of a triangle, it will equal the summation of squares of the two legs. So a couple of reminders about the Pythagorean theorem. It only works with right triangles. This theorem doesn't work with any other triangle. So there must be a right angle, and that's a fancy way of saying a 90-degree angle must be somewhere in the triangle for it to work. C is always the hypotenuse. So whenever you use the letter C in the formula, make sure you're talking about the hypotenuse. The hypotenuse is always the longest side of a triangle and the one that's across from the 90-degree angle. And A and B are the legs, and it doesn't matter which leg you call A or which leg you call B. But what is important is realizing that the hypotenuse is always C. We're going to do 3 examples, starting with this right triangle. First of all, there is a 90-degree angle right here, which means I can apply Pythagorean's theorem. C squared equals A squared plus B squared. I write the formula first before I start calculating. I got to identify what the hypotenuse is. The hypotenuse is always the side across from the 90-degree angle, or what appears to be the longest side of the triangle. And that's the side I don't know. So basically, I'm solving for C. 5 and 12 are the legs. Now, it doesn't matter which leg I call A or which leg I call B. I'm just going to call 5 leg A, and I'm going to square it. And I'm going to call 12 leg B, and I'm going to square it. And now, using my memory of perfect squares, 5 squared is 25, and 12 squared is 144. Now, I'm going to add up those numbers. 25 plus 144 is 169. And this is where a lot of students think they're done. They think they've finished because they got one number here. However, it's not reasonable to think that the distance from here to here would be 169. Remember, our goal is to solve for C. And in order to do that, I have to get rid of the squared. So what am I going to do? I'm going to square root both sides of the equation. The square root of C squared becomes C, and therefore I've solved for C. And 169 happens to be the perfect square of the number 13. And I'm going to box in my final answer. Let's move on to example 2. In this example, I have another right triangle. My right angle is right there. And this that I'm highlighting is the hypotenuse of the triangle. In this example, I know the hypotenuse. It's the leg that I'm looking for. So I'm going to write the formula, and I'm going to plug in the numbers here. 5 is the hypotenuse, and C is always the hypotenuse. So I'm going to have 5 squared. A, I'll call that one A. That'll be 3 squared. And I don't know B. I'm looking for B. I'm looking for this leg. 5 squared, 25. 3 squared is 9. And what I'm looking for is B squared. Now I'm solving for B. To do that, I'm going to apply algebraic steps to both sides of the equation. I'm going to subtract 9 on both sides. That cancels that out. 25 minus 9 is 16. And that equals B squared. And once again, this is where some students think they're done, but you're not done. It's not reasonable to think that the leg would be 16. Remember, the hypotenuse is the longest side of a right triangle. So there's no way that this can be 16 because that would mean it's larger than that one. Remember, we're solving for B, and I have B squared equals 16. So I have to square root both sides to get my answer. That undoes that. And now over here, the square root of 16 is 4, and that's my answer. Now, for a quick second here, I want y'all to realize that for these questions, we got what are known as Pythagorean triples. Pythagorean triple is when all of the sides are natural numbers, like 5, 12, and 13, or 3, 4, and 5. Or in other words, all of the sides, the answer was a whole number. That does not always happen. There are 4 triangles that you should memorize as the famous Pythagorean triples. Now, there's many, many, many Pythagorean triples that I didn't include here, but here are 4 of the most famous ones. A 3, 4, 5 triangle, a 5, 12, 13 triangle, an 8, 15, 17 triangle, and a 7, 24, 25 triangle. These triangles show up often on geometry assignments and other Pythagorean theorem assignments. The next example and final example that I'm going to do is using Pythagorean theorem to solve an isosceles triangle. Now, an isosceles triangle means that this side is the same length as this side. And since those sides are the same length, this angle is equal to this angle. Well, this is a 90-degree angle, and all of the angles of a triangle add up to 180. That means this is a 45-degree angle as well, and this is a 45-degree angle. So this is a very common triangle that we're going to be dealing with in pre-cal. So Pythagorean theorem says c squared equals a squared plus b squared. And the only thing I know here is the hypotenuse being 12. So I'm going to do 12 squared equals a squared plus b squared. Now the problem with this is I only have one equation and 2 unknowns. However, since both sides are the same length, instead of calling one a and b, I'll just call them both a. And so I'm going to have 12 squared equals a squared plus a squared. That means because they're the same side, I'm basically assuming A, and C, right? Well, a squared plus a squared, that's 2a squares. And now I can solve for a. 12 squared is 144. On the right side, I have 2a squared. How do I solve for a? Well, the first thing I'm going to deal with is I'm going to deal with this multiply by 2 by doing the opposite. I'm going to divide 2 on both sides. 2 divided by 2 is 1, and therefore I get a squared on the right side. 144 divided by 2 is 72. And, my friends, am I done? Of course not. I'm solving for a. I'm not solving for a squared, I'm solving for a. So I have to do the square root on both sides. Now, you might be thinking to yourself, oh my gosh, there is no square root for 72. And yes, there is a square root for it. As you can see here in Desmos, the square root of 72 is this irrational number, this number that goes on and on and on forever. So technically, we're done. We could say that the square root of 72 is what a is. So 8 point something something something. However, we don't like to have big square roots like this. We like to simplify square roots, and let me remind you how to do that process. I know 72, that's the same thing as 36 times 2, right? There's no difference between 36 times 2 and 72. Well, 36, that's a perfect square. And I know the square root of 36. I don't know the square root of 2. So I'm going to write the square root of 2, and then I'm going to write the square root of 36, which is 6. And that right there is how we want to show our final answer. As you can see here in Desmos, 6 times root 2 is the same exact thing as the square root of 72. I take it that mathematicians preferred to write it like this because mathematicians had common square roots written down somewhere. And if they would just go to their square root of 2, which is about 1.4-ish, and multiply it by 6, they would know what the value is.